Okay, we are off to skip ahead a little bit to chapter 10, which is about energy, and we'll eventually come back to all those chapters we skipped. Chapter 10 here, which is about energy, should be the last chapter that will be included on our exam, which is coming up next week, I believe. A week from Wednesday is our first exam on chapters 1, 2, 3, and 10. We do also have a quiz coming up this week on chapter 2 on Wednesday, I think. Yes. So again, we'll do that at the beginning of lecture on Wednesday. We'll hopefully knock out the rest of chapter 10 as well afterward. All right. So chapter 10 talks about energy, and we talk about different types of energy that we calculate energy, and also the way that energy is sort of displayed when we have chemical reactions or any of those type of things that do occur. So let's talk about it here. So when we do talk about energy, which as we'll see is really sort of a law of thermodynamics, and as we will also see, and we've probably talked about it already, the idea of the law of conservation of energy. Usually when we think about energy, it's always the idea of sort of a perfect transfer of energy. So the idea is if somebody sort of loses a certain amount of energy, somebody else will gain the same amount of energy. And there's really kind of two things that we look at usually when we're doing some type of chemical reaction, and that is the system. And the system is essentially any part of the universe that you're interested in. So when you're doing an experiment, for example, in lab, and you're doing it in a test tube, your test tube's your system. If you're doing it in a beaker, your beaker your system. And then pretty much outside of the system is the surroundings. And again, that same sort of example, if you're doing some type of reaction or something inside the test tube, then everything outside of the test tube is considered the surroundings. So when we're talking about energy in this chapter, we will talk about it, as it goes from, say, a system to the surroundings. And also don't forget that the surroundings, for example, can also send some energy into the system. So once again, though, one thing to sort of keep in mind is this sort of nice, perfect transfer of energy. So for example, here, if my system was to lose 5 kilojoules of energy, my surroundings then should be the one that picks up that 5 kilojoules of energy. And that's part of the law of conservation of energy. We don't lose it or create it, but it can be sort of transferred from one spot to the next. So when we talk about systems, there's different types of systems that we deal with. And an open system, much like the name would imply, is something that you can take mass out of. You also can see the exchange of energy with the surroundings, like an open beaker or something like that, or an open flask. You could reach in there, maybe not with your hands, but you could go in there and you could take out whatever's in there in terms of the mass. And also energy can exchange between the glass flask and the surroundings as well. A closed system is also what it sounds like. And you kind of throw a stopper in it and close it up. You no longer will lose any mass from the inside, right, as it has no escape route. But you still have sort of that exchange of energy from the system to the surroundings. And lastly, an isolated system, pretty much where there's no transfer of mass or energy in the system. Everything sort of happens sort of inside, so it's not really affected by anything that's happening in terms of the surroundings. We'll see a little bit later on this chapter, but for example, one way that they calculate, the calories in your food is they throw it into a chamber like that, where it's sort of an isolated chamber, and they set it on fire, and they basically measure how much energy is coming off of it. It's not affected by any of the surroundings or anything like that. The mass doesn't come out, so a very isolated type of system. And here are some pictures of those types of systems. Once again, kind of an open flask. We could take, what's in there in and out, and also have that heat transfer. We also, if we put a stopper here, we'll have just the heat transfer, and an isolated system. Once again, pretty much everything's happening inside, sort of independent of what's going on in the surround, not really affected by the surroundings at all. And so it gives you a good way to measure something specifically in terms of energy, for example, what's happening just based on, say, a reaction of what's going on inside. So when we talk about energy, energy is the capacity to do work, is force times distance, and there's different types of energy come across. So for example, there's chemical energy, and that's the energy that's stored in the structural units of chemical substances. Now, when we have something like bonds and we make bonds and breaks bonds, there is energy associated with that process. So if I had a bond like this and I wanted to break this bond, would I need to put energy into it or take energy out to break bond? What do you think? You would have to put energy in, right? So we got a nice bond here. When we put energy in, everybody gains energy and they get enough energy, kind of wiggle away from each other. Not exactly how it happens, but maybe close. And they get enough energy really to separate one from another. Also, when we make bonds, it is a process where we have to release energy. So if you think about it, everybody's got a lot of energy. As they release energy, they kind of slow down and they're able to bonds. So even the process of breaking bonds and making bonds, which is essentially what happens when we have a chemical reaction, it has to do with energy. And once again here, if we were to make bonds, that is energy being released. I think we've touched upon this before, and we'll see it a lot in this chapter. That is a process, right, that is known as being exothermic, when heat and energy is sort of released. And when we break bonds, that is the process where energy is absorbed. And those type of processes, as we've probably touched upon, I'm sure, is known as being endothermic. So exothermic and endothermic are obviously two very big words here that we'll see a lot in this chapter. And again, really sort of describe what's happening in terms of the energy. And since we do have this sort of nice, perfect exchange of energy from one place to the next, either the system to the surrounding, surrounding to the system, it is exothermic in most cases for one thing, either the system or surrounding, and is the opposite for the other. So either exothermic or endothermic. So for example, if we have a reaction that's giving off energy, that's going to be exothermic. And for the surrounding, it will be endothermic, right? Because it's going to be picking up all that energy, and vice versa. If we have a endothermic reaction, it's got to pick up that energy from somebody, and it will be exothermic for the surroundings basically coming in to do that. We can recognize, right, whether or not a lot of times if a reaction, say, is exothermic, thermic, just by feeling, like, say, the test tube. If you happen to be holding it, not a good idea in certain experiments that you do to actually hold it, should probably be in the test tube rack. But let's say this is my test tube, and I hold my test tube, and my test tube starts to feel really cold. What type of reaction is happening in my test tube? It is an endothermic reaction, right? So it is basically absorbing energy. The only place it has to absorb energy is my hand, right? So all the heat from my hand is going into the test tube, thus it feels really cold. Opposite of that, if I'm holding on my test tube and it starts to feel really hot, that means that the reaction inside is exothermic. It's releasing all that heat and energy to my hand that's holding it, right? And that's why, again, it feels hot. Also, again, how those hot pads, cold pads that you kind of break do a reaction and it gets hot or cold, sort of function as well. Now, when we talk about different types of energy, there's also potential energy, and that is the classic idea of something possesses a certain amount of energy based solely on its position. And that is like our classic example of the big giant boulder there that's about ready to sort of fall off the hill. So because of its position, it contains a certain amount of potential energy. And obviously, energy can be transformed into other types. As it comes down the hill, it will kind of transfer to kinetic energy, some of that. And that's the energy of motion. Obviously, once it hits, it will transfer some of that energy to our ground or whatever happens to be. And it will come to rest at a difference in energy from where it started, right? It started at a certain amount of potential energy, different amount of potential energy. So once again, this idea of conservation of energy is just that we don't create it, we don't just from one form to the next. And again, we sort of think of it as sort of either to the system, to the surroundings. Now, speaking of thermodynamics, thermodynamics really is the study of the interconversion of heat and energy. As you continue on your chemistry journey there to Chem 1B, you'll have a whole chapter on thermodynamics that covers a lot of other things. So some parts of thermodynamics that you'll cover when you get to 1B deals a lot with the idea of spontaneity. And when we talk about a reaction being spontaneous, based on thermodynamic sort of properties, what we're really saying, and a lot of times people have a misunderstanding of sort of that word spontaneous. Sometimes people think, oh, this reaction is spontaneous, so you snap your fingers, it's going to happen really, really fast. And that's really not what spontaneous means in the case of thermodynamics. If something is determined to be a spontaneous reaction, it basically means that under those conditions, you would expect that reaction to actually occur. So that's what basically spontaneous means. It could occur really fast. There's lots of spontaneous reactions, for example, that occur really, really slow, and there's some that occur really fast. Something else that you're learning when you get to 1B that deals with how fast or slow a reaction sort of is kinetics of the reaction. So when you study kinetics, that's how fast or slow a chemical reaction is. But thermodynamics a lot of times tries to answer that question, whether or not a reaction will basically occur. Our sort of purpose here of thermodynamics in this class and probably the next class that you take is more the energy component of thermodynamics. And really the law of conservation of energy is really known as the first law of thermodynamics. So that's sort of the first law of thermodynamics, which kind of deals with the energy component of, again, we don't create nor destroy any energy along the way. So there are certain values that are what are referred to as being state functions. And state functions are really properties that are determined by really two important things. And those two important things are basically where you start and where you finish. Those are really the most important things when you're dealing with state functions. And energy, pressure, volume, temperature, these are all sort of state functions. And what that means is, for example, if we look at our hikers, they both started over here and they both ended right there. In terms of their potential energy, they're basically the same at this point because they both started in the same location and they both ended in the same location. So the only two really important things is where you start and where you end. And it doesn't matter, for example, here that the red hiker took the scenic route up the mountain and the blue guy took the more direct route up the mountain. In terms of their potential energy, they basically will be the same because they initially and finally ended at the same location. So the importance of that is, for example, when we look at a chemical reaction, we have our reactants that go to our products. And the book kind of assumes that we've already talked about this since this is chapter 10, I suppose. And our reactants are our starting material. And obviously our products are what are formed as a result of a chemical reaction. So when we calculate things like energy, change in energy, change in pressure, change in volume, change in temperature, and that's what the little delta symbol means. It means change. We basically take the final minus the initial to figure out what it is. And when we deal with chemical reactions, we oftentimes will calculate something like energy by taking all the energy of our products that we made and subtract it from all the energy of our reactants. And when we think about a chemical reaction, our products are really our final state, and our reactants are really our initial state. So a lot of times, and as we'll see in just a second, a little bit down the road here, delta H, which is the change in enthalpy, and that is a fancy word. basically meaning the heat of a reaction, how much energy is either given off or absorbed in a reaction. And the way that we calculate it is pretty much that way. We take all the energy of our products and we subtract it basically from all the energy of our reactants. So again, our final state minus our initial state. Another really important thing in terms of energy and chemical reactions is, again, not all reactions happen in like a one-step process, like all the reactants just go directly to products. A lot of reactions actually occur in many individual smaller reactions that when you take them all together gets you to your products, basically. And in terms of energy, energy is sort of additive in that sense. It doesn't matter, again, like the guy taking the scenic route up the mountain, that if it took you 3, 4 little reactions to get to your products, or if it took you 2 reactions to get to your products, in terms of the energy, you basically just add them all up. And basically where you start, where you end with will be accounted by all that energy that happened along the way. And that is basically kind of what a state function is. Any questions on that there? So let's talk about some important units here of energy and some that we will use throughout here this semester. And a reminder that none of this is negative, so that's just from PowerPoint here. So we'll just kind of get rid of some of those guys there. First off, I would say probably the most common units of energy that you use the most in chemistry is actually a joule. And 1 joule, by the way, is equal to 1 kilogram meter squared second squared. This relationship is a good relationship to remember. I would say maybe not so much for this class, but definitely in the next class, you'll see that relationship a lot. And there's a lot of formulas where you have to kind of take that into account when you're doing it. We won't see too much of it in here, but definitely a joule and a kilojoule are 2 very common units of energy, and 1,000 joules is equal to a kilojoule is definitely something that you do need to know. Other common units of energy that are used is a calorie, and that's a lowercase calorie in terms of a lowercase c. And we'll talk about what I mean by that in a second. The definition of a calorie is basically the amount of heat or energy that's required to change 1 gram of water. So that's sort of the definition of a calorie. And the relationship between calories and joules is also something that you need to know. 1 calorie is 4.184 joules. And that number of 4.184 joules is an important number. We'll see a little bit later on. That is what's also known as the specific heat of water, which is a value that you need to know as well. So it's good that is the conversion factor actually that you use. I would say that in addition to kilojoules and joules, calories and kilocalories are also common units. So 1,000 little calories is equal to 1 kilocalorie. So what do I mean by sort of little c? There is also a calorie that is a capital C. I'll write it like that for dramatic purposes. 1 capital C calorie is actually 1,000 of the little calories, little c, and that's also 1 kilocalorie. This is also sometimes referred to as a nutritional calorie, like your calories of food and stuff like that is basically what that is. So you don't want to confuse those. If you actually do see a capital C, it is not the lowercase c. Most of the time in chemistry, we usually will focus in on the lowercase there, unless we're nutritional type calories. But that is, again, some conversions that you should be aware of. One way that we use energy is to change the temperature of a substance. We also use temperature as a gauge of what's happening with energy, right? And the flow of like heat and energy. By the way, the heat flows from hot to cold, cold to hot. Which way? It is hot to cold, right? So we might have talked about it, right, when we were talking maybe about ice cubes, when we were talking about phase changes and stuff like that. Again, when you take out an ice cube and put it on the table, the room temperature is hotter than the ice cube, right? So all the energy from the room temperature air flows into the ice cube, right? From hot to cold. And that melts your ice into water. You then like take that liquid water and you put it into the freezer. At that point, the liquid water's temperature is actually higher than the temperature in the freezer. So all the energy from the liquid water starts to escape, right, to the freezer air. The result of that is the liquid water loses energy, right? And it just kind of clumps into ice at that point. So again, we always have that flow of energy or heat for sure going from the hotter guy to the colder guy. One way that recognize what's happening in terms of the flow of energy is to simply stick a thermometer in something, right? And look at what is happening with the temperature as, say, a reaction is happening. If something is exothermic, would to go up or down? Yeah, so if it's exothermic, it's going to be releasing energy, right? So what we would expect to see in terms of the temperature of that object is temperatures start to drop, right? Because it's releasing that energy. It's going to be cooling down. Like if we took a hot piece of metal, right, and we threw it into room temperature water, the hot piece of metal will cool down. And opposite of that, right, we would see that the water's temperature would increase. So something that is an endothermic process happening, we would actually expect the temperature of that thing to start to rise. Like that example again, I put in that hot piece of metal in that water, temperature of the water should go up, temperature of the metal should go down, as one is exothermic and one is endothermic. Once again, in that situation, if we did throw that hot piece of metal into that water, whatever energy that is lost by the metal is really what the water's picking up in that case and responsible for the temperature change that you're seeing basically in both of them. Any questions on that there? So that brings us to thermal energy, and thermal energy is the energy that's associated with the random motion of atoms and molecules. And when we talk about thermal energy, it is related to how many molecules and atoms there are. The greater the number of atoms or molecules, the more sort of vibration, the movement that you're going to have, going to result in something where you have less numbers of molecules kind of moving around. So an example to illustrate the difference between, for example, thermal energy and temperature. Let's take a look at this example here, which is, we have a bathtub of water. So it's pretty big, I would imagine. And it's at 40 degrees Celsius. And we got a little coffee cup of water or coffee that's at 70 degrees Celsius. Now, when we look at each of these situations, the one that should have the more thermal energy is actually the bathtub, right? Because in comparison between the bathtub, how much water is in there versus how much water is in the cup of coffee, there is a ton more molecules, right, in your bathtub. And it would have a lot more thermal energy because it has a lot more atoms moving around and vibrating. But temperature, in your opinion, might reflect that, oh, wait, shouldn't the other guy have more thermal energy because it has a higher temperature? And again, there is a distinction between temperature and thermal energy. We use temperature to measure sort of what's happening with the energy, but it is not really what thermal energy is. The reason why the coffee cup has a higher temperature is a lot less water in there, right? So takes a lot less energy to increase the temperature of it versus this. So kind of like if you were to take a small little glass of water, a little bit of water in there, and you put it on the stove and you started to heat it, it's going to start to heat and temperature is going to rise a lot quicker than if you got the giant pot of water to make pasta in, right? It takes a lot longer to heat that up because there's a lot more water molecules involved. So it takes a lot more energy to do that, to see a big increase in the temperature than what we see over there. So since there's a lot less water molecules than the guy on the right, we actually can achieve a higher temperature. But in terms of thermal energy, the guy on the left there, which is their bathtub, has a lot more molecules. It will have a lot more thermal energy. Questions on that there? By the way, as we will also talk about here when we talk about specific heat capacity, something like water, for example, requires a certain amount of energy to be put in there per gram of it to just move its temperature by 1 degree Celsius. So clearly something like the bathtub has a lot more water molecules, a lot more grams of water, which means you got to put a lot more energy in there just to see a little bit of a temperature change. The guy on the right has, again, a lot less water molecules, which means not as many grams of water, which means you don't need energy to see a bigger temperature change, and the temperature will change a lot quicker because of that. So heat, as we talked about, is that transfer of energy from hot to cold. And again, our exothermic process is any process that gives off heat to the surroundings, or basically releases heat or energy, like striking a match. Again, obviously, if you strike a match, light your Bunsen burner, those are all exothermic processes. You could bring your hand near the fire, not on the fire, but near the fire. You can feel the heat coming off of it. And again, that's your hand picking up all the heat and energy that's being released by that combustion reaction that's happening, say, with a Bunsen burner or something like that. Again, that endothermic process absorbs energy. And also, again, why you hold on to an ice cube, for example, in your hand feels very cold, right? Again, the ice cube is lower temperature than your hand. Again, it's going to suck out all that heat and energy from your hand, which is why you feel cold. Also, why you feel cold when you get out of the pool, right? When you get out of the pool, you have a lot of water on you, or to shower, right? Have a lot of water. Going to increase the rate of evaporation on your skin, which means all the heat's coming out of your skin, right? To try to evaporate all that water molecules you have in there, you start to feel really cold. Also, why when you take a shower that's like a hot shower and there's a lot of steam, or you're in the steam room or something like that, all that steam wants to go through condensation. Why the mirror gets all wet, right? It's because there's a lot of condensation happening. Process of condensation, right, is going from gas back to liquid, which is exothermic. And that's going to be releasing a lot of energy in the room. You're standing in the room, you feel warm, right? And so that's why those things happen. Also why we sweat, right? Cool our body down as that sort of process is occurring. So when we talk about exothermic processes and endothermic processes, what we will see here throughout this chapter and in general, when we calculate each of these things in terms of energy, there's really kind of two types of energy values that we commonly will see in this class and in most classes. That change in enthalpy, that delta H, and Q. Q is heat or energy. These are two types of values that we oftentimes will calculate in terms of energy. And when it is an exothermic process, each of these values are typically negative in nature. So if you calculate something and energy and you end up with a negative value for that energy component that you do, it is a exothermic process that's happening. Or somebody just straight up tells you, hey, the reaction has a delta H of negative 400. As soon as you see that negative, you know it's an exothermic type reaction. Now, for endothermic processes, these two common sort of energy values actually are positive values. We're going to talk why that is in a second, but they will end up being positive values. So once again, if you calculate energy, which is this chapter and throughout your chemistry career, it is really important to make sure you don't just disregard the negative sign, for example. So if you do the calculation, you get a negative number for energy, it's actually really important to keep that negative number because it tells people when they see it that what is happening is an exothermic process and heat and energy is being released. If you get a positive number, clearly you should keep it positive. That's usually not an issue. But the positive actual number that you get also tells people that what is going on in that particular case actually a endothermic process and heat and energy is being absorbed. So a lot of times when they do calculations of energy, sometimes they should keep the negative, get rid of the negative when they're doing those type of things. And you definitely should always keep it, especially when you're doing energy, because it gives you, honestly, in most cases, it gives people a better idea of what's going on in terms of thermic and endothermic than the number. The number oftentimes is irrelevant. It's actually the sign that you have for energy that's really important. Any questions on that? So let's take a look at these two things here. And these two things are what are referred to as energy diagrams. And there's two different types of energy diagrams that we see here. One's an exothermic reaction and one's an endothermic reaction. And there's some important parts of each of these diagrams. On the Y there, we have our energy. And on the X, we have basically the progression of the reaction that's happening. So when we look at the guy on the left here, which is exothermic, these are our reactants, which once again, as I mentioned before, is your starting material in a chemical reaction. And products is what is formed as a result of that. And over here, we have our products. So when we look at the energy location of our reactants to our products in this case, we see here that reactants are actually higher in energy than our products. So the only way, if you want to think about it this way, for our reactants to get down there to our products in terms of energy, is energy has to be given off. So whenever you see any type of energy diagram like this, that the reactants are actually starting higher in energy than where the products end up, it's always going to be an exothermic reaction, and net the reaction is going to basically give off that energy. If we look at the diagram there on the right, this is an endothermic where this is our reactants, where they're starting in terms of their energy. This is our products, where they're starting in terms of their energy. And we actually see the opposite here. The reactants are actually lower in energy than our products. And the only way for our reactants to get up there to our products is energy has to actually come in to do that. And energy would be absorbed in this case, which is why it would be an endothermic reaction. Now, let's talk a little bit about sort of what is happening for the rest of these diagrams here. Really, what is happening when we have a chemical reaction. So a couple of things that's important to remember, that in a chemical reaction, the only thing that happens is basically bonds are going to be broken and bonds are going to be made. We always have sort of the conservation of elements, which means if we start with 4 carbons on a reactant side, we end up with 4 carbons on the product side. The only difference happens as a normal chemical reaction takes place is when we get our reactants, we're basically just going to break all these bonds. And bonds only really involve electrons. And on the product side, we're going to make all these bonds. So for example, if we took something like a little H2 plus some O2, make some water, do a little balancing like I'm a good chemistry person there. What's going to happen here is our H2 and our O2, we basically have these guys together like so. And it's going to go to the other side and make a couple of waters here. And what is going to happen is, as this reaction starts, we're going to start breaking these bonds. We will also start making some bonds along the way. And eventually they will make these new guys. We have the same elements on both sides of the arrow, but they're bonded differently. We made substances, like we talked about with chemical changes, and that is obviously a reaction happening. So the process on the reactant side, it's actually happening as you kind of go up this hill that you see in this picture. So as you come up this hill to sort of the top there on both of these guys, that is essentially what is happening. We're starting to break and make bonds. So what happens when we get to the very top of the hill? When we get to this very top of the hill, this is what is sometimes referred to as a transition state. So at the very top of the hill here, this is what is referred to as the transition state. And up there on the transition state, you will have what is sometimes referred to as the transition state complex. are sometimes referred to as the activated complex. So what is this guy? Well, this guy is pretty much what we have happening as we go up the hill. We have this sort of substance at this point, at the very top of the hill, the highest point in energy. We have a substance that has partially broken bonds and also partially made bonds that's happening. They haven't fully broken and they haven't fully made. It's sort of that transition point, hence the name, of getting to our products. About energy is when we have things that are in high energy. Is that really what things want to be? Do things want to be in high energy or low energy? Which one's more? It's actually low energy, kind of like us, right? We want to be in low energy most of the time, not so much high energy. So things that are really high in energy are not very stable. And that thing at the very top, that activated complex, transition state complex, because of its partially made bonds, partially broken bonds, is very, very unstable. It actually will not hang around a really long time. It will very quickly drop down the hill to the other side and make our product. So very quickly, sort of what will happen usually is this thing will, just kind of head down the hill here to our products. And usually that transition state complex is something that is really, really hard if you were trying to isolate it by itself. Because it's so high in energy, it's really unstable. It doesn't hang around a really long time. It makes it really, really hard to sort of just isolate that thing at the very top of the hill. Pretty much everything that happens in chemistry in the terms of energy is in an effort to minimize the overall energy for everybody and get them to kind of a lower state of energy. And that makes things much, much more stable. Although in some of these reactions here, it looks like we net some more energy than we started with. But overall, if we looked at all the individual components of a reaction, everybody through bonding kind of brings themselves to a much better state of energy than where they started. Any questions on that there? So let's talk about some other important parts of this. And since I scribbled all over this, I'm going to redraw a couple of these diagrams here. So I'll draw an exothermic and an endothermic one. So here we'll have our energy. Our reactants and our products. And this obviously would be our exothermic. And we'll draw one over here for endothermic. Okay, so there's a couple of really important parts to these curves as well, and it has to do with that hill. And if we look at that hill, which is basically where the reactants start in energy, see like the very top of that hill, that is what is known as the activation energy. And that is sometimes abbreviated as an E of A. And the activation energy is the minimum amount of energy that's required for a reaction basically to take place. So it's like the minimum amount of energy that you need for this reaction to take place. And for this one here, it would be like here. Energy. So as I mentioned, in a chemical reaction, what basically happens is bonds break and bonds make. In order for that to happen, really a couple of things need to sort of occur for products to be made. They actually need to collide with each other. So the atoms, the molecules on the reaction side has to come in contact with each other. And believe it or not, they actually do need to hit each other in the right spot, like the activated spot. If they collide in the wrong spot or with the wrong amount of energy, you actually will not make products. So just because two things sort of come together doesn't mean that they'll break apart and start making products. They actually have to hit each other in the right location. And the second really important thing is they got to hit each other with the right amount of energy, which is like that activation energy, that hill that they have to climb to get to the other side. And that hill is really what stands between reactants being able to make products. there will be a certain amount of reactants that will have enough energy to do that, plenty of energy to get up and over the hill. And there'll be a certain amount of reactants that don't have enough energy to get up and over the hill to the other side. That hill also plays a really big role in how fast or slow that reaction may take place. If I have a really big activation energy hill, would you expect that reaction to occur fast or slow? Slow, right? It's like a big hill. If you had to climb a big hill, not a lot of people would want to go up and over the hill to get to the other side. But if you had a smaller hill, like a little speed bump in the parking lot, not a big deal, up and over the other side, everybody's got probably enough energy to do that. It's not going to take long to do. It's going to be a much faster reaction. So that activation energy, depending on the size of it, plays a really big role in terms of whether or not the reaction will occur fast or slow. Another really important location on these graphs here is really the energy difference between where the reactants start and where they end. And that is what is known as the delta H of the reaction, that change in enthalpy that we were talking about earlier. So once again, in a reaction, products are where you end, your final state, reactants are where you start. So the way that we calculate delta H for a reaction is to take the delta H of our products minus the delta H of our reactants. So when we look at our products here versus the energy of our reactants, our products are lower in energy than our reactants, which means in terms of numbers, the product should actually be a smaller number than our reactants, which should be a larger number. What happens when you subtract a smaller number from a larger number? You end up with what type of number? Negative, right? 2 minus 4, you end up with -2, right? And that is why we said a second ago that delta H's that are negative imply that the reaction is actually going to be exothermic for that region. And that is why we expect this guy to end up being a negative value for exothermic. Now, if we look at that same sort of situation over here for our endothermic, that is the energy of our reactant. That's the energy of our products. Once again, the difference between those two is our delta H of this reaction. So if we do our delta H of our reaction, which in this case, again, is our delta H of our products, our final state, minus delta H of our reactants, the initial state. If we just look at our locations of these two things, in this particular case, our products are actually higher in energy, which means it should be a larger number than our reactants. So in this case, we're actually going to take a larger number minus a smaller number. And when you take a larger number minus a smaller number, you end up with what type of number? A positive number, right? If you take 6 minus 2, end up with 4, you'll end up with a positive number. So this is the reason, and these diagrams help you visually see why when you have a delta H value that's negative, it's going to be exothermic, because it should result again in overall that energy being given off. And here a positive value for delta H will be an endothermic reaction. Any questions on that? Now, before we leave this, since we have it here, let's talk about, we talked a little bit about how fast or slow the reaction would happen. And it's based on that hill. So let's just say that we wanted to speed up a chemical reaction. So one way that we could speed up a chemical reaction is to add a catalyst. And a catalyst, when you look at an equation, is typically written on the arrow. So maybe they'll have like a metal, maybe they'll have something like H plus written there, which means it's an acid catalyst. But what a catalyst is and is not is a catalyst is not a reactant. It is actually not a product, and it does not get used up in the reaction. So a catalyst not a reactant, not a product, doesn't get used up. It is there simply to facilitate that reaction happening much more efficiently. So it finds sort of an alternative, more efficient pathway for that reaction to occur. The result of that is the reaction will occur oftentimes faster. So why does that happen? Let's just take an example. If we have a reaction where we have gas molecules flying around, and without a catalyst present, those gas molecules flying around has to depend on flying around and eventually coming in contact with the other gas molecule, right, for the reaction to take place. Could take a really long time as they're just kind of having a good time flying around in space before they kind of come in contact with each other in the right location, the right amount of energy. Now, let's say we flip into that reaction. The gas molecules are attracted towards the metal. That will now put all the gas molecules very close to each other, and that's going to allow them to start reacting a lot quicker. It also aid in the reaction happening as well. But that'll allow them to react a lot quicker than it would if they had to just kind of wait for it to happen as they're floating around. So you could think of a catalyst finding an alternative pathway, and it does affect the actual activation energy kill. I think of like the Roadrunner cartoon. Yeah, Roadrunner, Wile E. Coyote. Yeah. Roadrunner gets to the big mountain, opens the trap door, goes straight through, right to the other side, closes it. Coyote doesn't do that, right? He hits it. He's got to go up and over it. So you can kind of think of the catalyst that it finds, instead of having to go up and over the hill to the other side, it finds like that trap door and just goes straight through to the other side. Going to allow a lot more people, right, to get through to the other side. You're going to have a greater proportion of molecules that actually do that. So ultimately, how a catalyst works is by finding that more efficient pathway for that reaction to happen, it will actually lower its activation energy. And once again, when that activation energy is lowered, what happens is, as I mentioned, you'll have a much greater proportion of molecules that's going to have the right amount of energy to get over that. It usually will result in more guys getting over the hill. At a time, if somebody asks you a general question of what does a catalyst do, it will speed up a reaction. You should also note, and you'll probably learn it as you go through different classes, but there are catalysts actually that will slow down a reaction. Those are referred to as negative catalysts. But 99.9% of the time, if somebody says, hey, what's a catalyst? They're looking for you to say it will speed up the reaction by lowering the activation energy. Any question on any of that there? All right, so here again is just some different looking energy sort of diagrams. These are our reactants, that's our products. So once again, reactants higher in energy than products, energy being given off. This is our reactants in this one, that is our products. Here, reactants lower in energy, so has to overall absorb some energy in this reaction. So a few final thoughts here, not really, but a few final thoughts on exothermic and endothermic, and a couple other things that we sort of consider when we talk about exothermic and endothermic. Clearly, we've talked about that exothermic releases energy, but when we think about the energy component of a reaction, we think of it as being a product when it's exothermic. So sometimes, and very rarely in this class, and most of the classes you'll take, people will actually just put an energy value on one side of the air. The energy value over here on the product side, that usually indicates that it's an exothermic reaction. So we think of heat and energy as being like a product. Opposite is true if we in an equation on the side. As being absorbed or added to the reactant, and that is considered a reactant. This will really come into play right there. Never too early to look at chapter 17 coming up the pipe there in May. We will talk about energy in terms of what happens with certain types of reactions. And in some cases, we have to think of exothermic as being like a product, the energy, and endothermic being a reactant. So that sort of idea of, we treat it like a reactant or a product, the energy or heat component, does come into play a little later on. We'll talk about. I would say 99% of the time, though, you will not see it written right in the equation, but you will have the equation, and next to it, I'll go, hey, the delta H is negative with a number, or they'll give you the delta H here is positive, and that's probably 99% of the time the way that if you're given a chemical equation or reaction and sort of the energy component of it, that is most often how it probably will display to you as sort of a delta H value. Once again, you don't want to confuse yourself in terms of the delta H value. Again, the number really doesn't matter. It is actually that sign that's the most important thing in determining endothermic or exothermic. Any questions on that there? All right, speaking of enthalpy, let's talk about how to officially calculate it in a second, but we'll take a look at this here. Here we do have an isolated system, and we have hot water and cold water at different temperatures. So again, the flow of that heat and energy is going to go from our hot to cold. The result of that, in terms of temperature, is we should see the temperature decrease there. And again, as this cold water side starts to pick up that energy, we should see our temperature start to increase there. And in this particular case here, we have all that motion there from the hot water side transferring that energy, and they will meet somewhere in the middle. In this case, add 90 and 10 together, divide by 2, it'll probably come to rest somewhere at equilibrium at the same temperature in this sort of isolated container, with the loss of heat or energy surroundings in this case. So again, everything that's happening is sort of reflective of what's happening in that particular situation. One of the easiest ways, as I mentioned earlier, and that you'll do in labs this week, and in most of the labs you do, sometimes people think, wow, energy, you have to have these really big equipment to figure out how much energy is moving around, but really like a thermometer is kind of all you need in a lot of cases, and following the temperature change is all you need to do in a lot of cases. You can really figure out for chemical reactions what's happening in terms of energy, exothermic or endothermic. So let's talk about enthalpy officially here. The change in enthalpy is, again, basically the heat absorbed or released by the reaction. Again, as we've been talking about, if you end up with a positive value for delta H, that's going to be an endothermic, and a negative value will be exothermic. How do we calculate it? We basically add up all the delta H values for your products, and then you subtract it from all the delta H value of your reactants. Once again, final state minus initial state is essentially what we're doing there. So where do you find these values? They would be found in a table, an enthalpy table, and you would find these table values, and they sometimes be referred to as the delta H of F, which is the change, the enthalpy formation. So let's just say, for example, I make up an equation here where we got, I don't know, 2A plus 4B goes to, we'll go with 6C. And if we go to this table, we look up A, B, and C, and then we have some values here, like A is, we'll just call it 15 kilojoules. B is negative 25 kilojoules. And C is, we'll go with 98 kilojoules per mole. And these would be values that you would find in this table. And this type of information would definitely be provided for you. Obviously, you don't have to memorize the table or anything like that. When we talk about using it like this, there's a couple of really important things that you want to always make sure you do. These are also sometimes referred to as thermodynamic tables. Usually in the back of chemistry books, you'll find a table that has delta H values. They'll have delta S and delta G values, which are some other thermodynamic cyber properties all together in the same table. It's really important when you go to the table that you find what you're looking for. And not only that you find what you're looking for, but you want to make sure that it's in the correct state. If it's a solid, liquid, gas, aqueous, because there will be different values depending on the state it is. Most people screw that up when they go to the table for something like water. They just find like the first water they see in there. And it could be gas, it could be solid, it might not be liquid. So you want to always make sure that you find it in the right state. Typically speaking, if you go to this table and you have something that is like an element or something like that, that in its natural state, that's uncombined. like hydrogen, oxygen, nitrogen, or any metal by itself. That's how they naturally come uncombined. They typically will have a delta H value there in the table of 0. So some of them will be zeros. So how do we calculate this? When we go to this reaction, for example, we do have to take into account what's referred to as stoichiometry of this reaction or equation. And those are the numbers that we find in front of each of these things, the coefficient. And these things are considered moles. Like this guy here, mole, MOL, the same thing. So when we do this, we're going to take our delta H and we're going to take all of our products. So in this case, we have just the C, and we do need to take that 6, and we need to multiply it by the value that we see in the table for C, which would be 98 kilojoules per mole. That happens to be all the products I have. If I had more products, then I would do the same thing for the other product, and I would add them together. So if there's more than one product, you just do the same type of calculation and just add up all your values there for your product side. So this takes care of our product side. I'm now going to do the same thing for my reactant side. So I have a 2 for my A. I'll go to my made up number there of 15 kilojoules per mole. Now I'm going to add it to my other reactant, which is 4 times the value there of B. And this basically takes care of all of my reactants. So what I'm doing here is basically adding up all the energy of my products and subtract it from all the energy of my reactants. We have to take the coefficients into account because, frankly, there's 2A molecules. So each one has a certain value. So if there's 2 of them, we need twice that. There's 6 C molecules. There's 6 individual ones there. Each individual one has the value in the table. So we have to multiply it by 6. So if we do that, we take 6 times 98. We then subtract it from 2 times 15. Maybe 2 times 15 plus 4 times minus 25. And if I did this all correctly, this is going to give me something like 658 kilojoules here for my delta H for this particular reaction. First off, any questions on that? Is this reaction endothermic or exothermic? It is endothermic because my delta H value here is positive. Yeah, so this reaction would be endothermic in my made up reaction because we have a positive value for delta H. Any questions on that one there? All right, so why don't we try with some ones here with some real numbers and see. All right, so here you go. On this reaction here, calculate the delta H. Also determine whether or not it is exothermic or endothermic. That again would be a thermodynamic table, and obviously again those would be provided to you. Okay, so let's take a look at this. So once again here, if it wasn't given to you, you would go find that table. A lot of times, again, in the back of the book, you could usually find this type of table. We're going to do our delta H for our reaction here, which once again, we're going to add up all of our products, delta H's from the table, and subtract it from all of our delta H's for our reactants. Once again, we do want to take into account the coefficients there when we do that. So let's see what we get here. Our delta H here going to be starting with our products. We have 2 of the sodium hydroxide, so we need to take 2 times the value of sodium hydroxide from the table, minus 470 kilojoules per mole. We actually have a second product here, which means we're going to take 1 times the value of H2, which as you can see is 0, as we talked about, kilojoules per mole. That basically takes care of all my products. I'm going to do basically the exact same thing with my reactants. I'm going to subtract everything there. And on our reactant side, we have 2 sodiums. So we'll take 2, bless you, times the value of sodium, which is 0, as it's in its natural state, uncombined. We will add it to our second reactant, which is actually water, has a coefficient of 2, times the value there of minus 286 kilojoules per mole. and that is going to take care of all of our reactants. So if we do all this here, basically it's 2 times minus 470. Then we're going to subtract basically 2 times negative 286. That's going to give me a delta H in this case of minus 368 kilojoules. First off, any question on the calculation there? Endothermic, exothermic? Which one? It is exothermic, negative value here, exothermic. So overall, this reaction is going to release that much energy. That is the difference between where the reactants and the products ended, right, in this particular case. Which actually would look like this, I suppose. All right, let's take a look at another one here and see. Maybe. All right, give this one a go here. Blow it up a little bit. There you go. Same thing, calculate the delta H here, and is it exothermic or endothermic here? Okay, so again, let's take a look. We're going to start with our products again, minus our reactants. All right, so starting on our product side, we got 16 of the COs. So that's going to give us 16 times the value of CO, which is minus 110. In this case, we also have 18 water, so we then need to add it to 18 times the value of water right there. Minus 286 kilojoules per mole. That essentially, again, is going to take care of all of our products. I'm going to write the reactants underneath there, but it is subtracting those reactants. And we got 2 of our C8. So we'll take 2 times the minus 208. And again, we got 25 oxygens, all going to give us 0 there, since that is this value. And now if we do it here, a little 16 times minus 110 plus 18 times negative 286, all subtracted from, actually, if I hit the button, that would work. There we go. Subtracted from 2 times negative 208, basically. And looks like minus negative 6492 kilojoules. And once again, this will be a exothermic, right? As we have a negative value here. Any questions on how to calculate delta H from just a reaction? Yeah. So technically speaking, I usually roll with kilojoules. You will see people write both, but really, technically speaking, these coefficients are the moles of each of these things. So technically, when we do this multiplication here, technically that's where the moles would actually be canceled out. I will say sometimes people will leave it, even the final answer, with the moles still there. I personally will just go with kilojoules, so I'm good with that, but some people will still leave it. But technically speaking, that's sort of where the moles would actually cancel out. Other questions? Okay. I think we'll skip this one. I think we get the idea, hopefully. All right. So the next thing we want to talk about is another way that we calculate heat and energy in a reaction, and this is specific heat capacity. And specific heat capacity actually has a definition very similar to calories definition. And the specific heat capacity is the amount of energy that's required to change the temperature of a substance, or 1 gram of a substance, by 1 degree Celsius. And there is a specific heat equation, which personally I use this one. Q is equal to ms delta T. Q is heat or energy, and it has basically units of joules or lowercase calories. M is mass, which has units of grams. S is actually the specific heat capacity, and it has units of joules per gram per degree Celsius or calories per gram per degree Celsius. So it has all 3 of those units. Now let's talk a little bit about that S, which is specific heat capacity. very common when people do this equation. They always flip those two things, the Q and the S. So the way to remember that is Q has 1 unit. The specific heat capacity has got all 3 units that are involved. So also in terms of that number or letter, I personally, once again, use S. Some books will use C for specific heat capacity. Some books will even use SH. So if you see any combination thereof, that is basically talking about specific heat capacity. Once again, I'll use S, but some books will use. It's basically the same thing. And now, unfortunately, here's our temperature. This is going to be in degrees Celsius. It is one of the few formulas in chemistry where you don't convert it to Kelvin. So we convert to Kelvin. Here's one we do not convert. Don't convert it to Kelvin. Leave it in Celsius. More importantly, though, is the change in temperature part, which should always be your final minus your initial temperature. And why that is really important is for this reason right here, which is if we look at this equation, our specific heat capacity is a positive number. Our mass is a positive number. And when we calculate Q and we end up with a negative value, that is exothermic. If you calculate Q and you end up with a positive value, that is endothermic. So the only thing here that will determine whether or not you will end up with a positive or negative value for Q is the change in temperature. So as we talked about earlier, if somebody, we would expect their temperature to go up, which means their final value of temperature is going to be up, larger temperature, nice. Is energy, their temperature value goes down, which means their final temperature value is smaller than where it started, which means when we take final minus initial, like we were talking about earlier, you will actually end up with a negative value for that. And that's going to turn your Q into a negative value, which is exothermic and what's going on. Always do final minus initial. And I say that because some people will just tell you, just take the difference. It's okay. And it is okay in the sense of you will get the correct number for Q in sense of how much energy either, but you won't know if it's being absorbed or basically given off. So when you calculate Q, as we talked about earlier, which is sort of a heat or energy sort of value, you should always make sure you have the negative there if it should be or not there, and it's really important. So I recommend strongly you always do final minus initial, and you'll be always, it will do the negative for you. So you don't even have to worry about, should I put a negative or not put a negative? So if you just do final minus initial, if the negative is supposed to be there and you do it correctly, you'll get the negative. And if it's not, you won't have it. So that's just the best way to do it. A really important number here is, and again, this is not negative, and this is a number that you should know. This is the specific heat capacity for liquid water. And that is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That is the specific heat capacity definitely for liquid water. And if you remember, that is also the conversion factor that you need to know, which is how we convert from calories to joules. So that 4.184 number is really important. The reason for that is, as I mentioned before, we want to figure out what's going on with energy. We need a thermometer, and a lot of times we simply just put it into the water and figure out what is happening in terms of the temperature of the water. Is it gaining energy? Is it releasing energy? And from that, you could actually figure out how much energy is happening in a chemical reaction. Because actually, when you do something like that, for example, at constant pressure, and you calculate Q, Q will be the same thing as the delta H for that reaction. It'll be the same thing as the change in enthalpy if you do it under constant situation. So simply just a thermometer, some water, and figuring out what's going on. And the reason we could do that for real chemical reactions as well, where you just take two solutions and pour them together, solutions are water-based, which means essentially we could just use the information with water and have a pretty accurate description of what's happening. Even if we took like hydrochloric acid, like sodium chloride or whatever might react together. That's a bad example, but two solutions that would come together. Any questions on that there? Yeah. What's that? Yeah, so that 4.184 joules is equal to calorie is specific. Perhaps what is the specific heat capacity for liquid water, which you do need to know for all your chemistry classes, including this one. You need to know that it's 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. It's basically this one right here. So you do need to know that along with the other version of it, which is calories per gram per degree Celsius. Okay. Now, I say it's important to distinguish that that is liquid water because, as you can see, ice and steam, different values. So much like most things, if you go to a table or look up certain values, you want to make sure that it is in the correct state. So if you were doing some type of specific heat calculation where you want to calculate, the energy associated with, something to do with ice changing temperature, you would need to use the specific heat capacity of ice versus the specific heat capacity of liquid water. So the state's really important, and water is an important one because it has all those three different states and it's very common. And we might look at all different states. So you want to make sure you do that. In most cases, you will use the liquid water version of it, and you would use that 4.184 joules per gram per degree Celsius. So what do these specific heat capacities really mean? They have three units, right? They have joules per gram per degree Celsius. That again is the amount of energy required to change 1 gram of the substance by 1 degree Celsius. If I have a large specific heat capacity, will it take less or more energy to change the temperature by 1 degree Celsius? It would take more, right? So the larger the specific heat capacity, the more energy you have to put in there to see that 1 degree change in temperature. The smaller, like gold over here, for example, 0.13, you only got to put 0.13 joules per gram per degree Celsius to see the temperature change by a degree Celsius. That is why water, for example, liquid water has a pretty high specific heat capacity. That's why people get upset when the ocean water changes by just a very small amount of temperature, right? If you think about how much water is in there and how much energy is needed just to tick it up that little bit, it's a lot of energy, right? And that's what, people get concerned about. And sometimes people go, just like a little degree move. But if you think about the enormous amount of water that's there and how much energy would be needed just to get it up a little bit, that's a lot amount of energy. Any questions on that there? I think it's probably a good place to lay it up, I think.